Hello everyone. So today we are back with another technique, that is linear discriminant analysis, or LDA. If you've learned PCA already, then you say that okay, I know dimensional reduction, but LDA is going to change you. You're thinking about it. It does something that PCA cannot do. Okay, so here's a real intuition about it. Imagine you have a bowl of mix of red and blue marbles, and you have to separate them out. You roll them down a ramp. Now the angle you tilt the ramp matters a lot. If you tilt it in the wrong angle, then both of them land in the same pill. LDA is the algorithm that can find the perfect angle for this, the one that make the red marble lands as far from the blue marble as possible, while keeping each of the other column having its own pill tight and compact. Okay, so that's LDA in a nutshell type. So more formally, LDA is a supervised dimensional reduction and a classification technique. It projects your high dimensional data onto a low dimensional space, but unlike PCA, it does this while maximizing the separation between the classes. So here's come the word supervised, that is the key difference. LDA know your class label and can use it. Now let me put LDA and PCA side by side because this comes up constantly. PCA is unsupervised. It has no idea about your class label. It only goal is to find the direction of maximum variance in your data. LDA is supervised. It actively used class label to find the direction that can better separate your classes. PCA can give you up to D components, where D is your number of features. LDA can give you at most C minus 1 components, where C is the number of classes. So if you have 3 classes, LDA will give you at most 2 discriminant access. So that's the actual strength, that you can get a very compact and a class aware representation using PCA for compression and the noise removal, while LD can be used for the classification and the visualization part. Moving forward towards the next section, we have the mathematical step-by-step algorithm. Okay, so I'll keep you visualizing with each of these steps. So LDA is built on two key ideation. The first one is the within class scattering, and the second one is between class scattering. Think of within class scatter as asking how spread out the data is around a class or its own center. If you plot all the red marbles, then how tightly they are clustered, and that's the within class scattering, and we'll capture it in a matrix called as SW. Now moving forward, we have between class matrix. It is asking the opposite, that how far are the class centers from each other and from overall centers of all the data. So that goes into a matrix called as SB. LDA's entire goal is to find a projection direction where SB is large and SW is small. In plain English, your class should be as far as possible but as tight as possible within themselves. Okay, to formalize this, we have something called as the Fisher criteria. We want to find a projection vector W that maximize the ratio of between the class variance to within the class variance. The formula is also given here. It's J of W equals to W transpose SB W divided by the W transpose SW W. Maximize this ratio, give you the best possible separation, and can solve this tune into a classic eigenvalue problem. Specifically, we can solve SW inverse time SB times W equals to lambda times W. The eigenvector with the largest eigenvalue are your linear discriminant. Okay, so now let's walk through the algorithm step by step. Step 1 is compute the mean vector for each of the classes. Step 2, build the within class scatter matrix SW by summing up the spread of each of the classes around its own mean. Step 3, that build the between class scatter matrix SB using the class means and the global mean. Step 4 is compute the SW inverse times SB. Step 5 is solve the eigen problem and get your eigenvalues and the eigenvector. Step 6 is sort eigenvalues from the largest to smallest and pick the top k eigenvectors, where k is at most c minus 1. Step 7 is that form your projection matrix W from these k eigenvalues and project your data. Z equals to x time W. So that's your new lower dimensional class separation data. So moving forward towards some of the scenarios also, that when should you actually use LDA is a few scenario, that when you want to visualize multiple class data in 2D or 3D while preserving the structures, then you can use this. PCA might keep variation but lose some of the class separation. LDA keep the separation as it is. Second, when you want a fast interpretable linear classification that scale to millions of samples. Third, as a pre-processing step before a downstream model like KNN or SVM. Your project, you can project your data to C minus one dimension first and then run for a classifier on it. It will be faster and often more accurate. There are a few important variant worth knowing. Quadratic discriminant analysis that relax the equal covariance assumption and give each class to its own covariance matrix, which create curved quadratic decision boundaries instead of straight lines. Regularized LDA handles the single SW problem by nudging it into slightly towards a scaled identity matrix. This prevents the inversion from blowing up. And the kernel LDA maps your feature into a high dimension kernel space before applying LDA. This will handle the non-linear boundaries. Okay. So here are written some of the common pitfalls that you can go over with. It's about the formula only, so it's not that much important. So all right, that with here we have covered about the objective function, about the Fisher criteria, maximizing between class scattering while minimizing within the class. We have also covered some of the core assumption that are the Gaussian distribution and equal covariance. If they break, then we can use the kernel LDA or the QDA. So that's all about the LDA. So thanks from my side. Yeah.